Hello again. So we last left off calculating entropy of real gases and real liquids. So now we're going to look at how entropy relates to spontaneity again, which was our original topic. Remember back we talked about these temperature gradients and vacuum pockets. Well, if we calculate entropy of that situation where the heat flow is from a hot to a cold, or cold to a hot, where it's separating. So the heat flow, if you're flowing from out of the cold into the hot, you get two sides of the pole, right? It flows from one half to the other. T1 is one half the pole and T2 is the other half. So if T2 is our surroundings and T1 is our system, and let's say T1 is cold and T2 is hot, no matter what. So cold, lower number, bigger number. Hot, T2 is bigger number, so you get a positive number. And if heat is flowing from cold to hot, flowing out of the system, it's negative. So negative, you get a negative entropy. On the other hand, if it's flowing from hot to cold to make the temperatures equal or similar, you would have a positive number, a positive entropy. So things that are spontaneous will have a positive entropy. Things that are non-spontaneous will have a negative entropy. Looking back to that vacuum, this vacuum process where gas spontaneously shrinks to create this vacuum would be an isothermal adiabatic system. Since an adiabatic, Q would equal, this is adiabatic, Q equals negative W. That's isothermal system. Q equals negative W, so entropy would be NR, because the T is taken out, ln V2 over V1. If the final volume is smaller than the initial volume, then we have a negative entropy. If a gas is expanded, we would have a positive entropy. So coming back to the second law of thermodynamics, isolated system, entropy always increases for a spontaneous process. It will always decrease for a non-spontaneous process, and entropy will always be zero for a reversible process. If the system is not isolated from outside heat and work, a spontaneous process could still see a decrease in entropy. So, which comes brings us to our Clausius inequality. So we can calculate, let's say, delta S, if we say for a reversible process, delta S equals 0. Spontaneous process, delta S is always greater than 0 in an isolated system. Remembering that du can be split into dq minus p dv, and for a reversible system, let's say dq reversible minus pdv equals tds minus pdv, because q reversible is the same, q over t is equal to ds. So send those two equal. That statement for reversible versus non-reversible. So this is for a reversible system, and this first one is for a non-reversible system. So again, the Q is on one side and the P is on one side. Let's say that Q reversible minus dQ is equal to P minus P external dV. Now, if the external pressure is greater than the internal pressure, which is our P, the volume will shrink, making P minus P external greater than 0. If the external pressure is less than the volume, then a gas will expand, making the right side of the equation positive. Well, making P minus P. Okay. If the external pressure is greater, this is a negative number, but the volume would contract. So a negative and a negative makes this positive. If the external pressure is less, P minus P external is positive, and the expansion is positive. So no matter what, the right side of this equation is a positive number. So no matter what, you're going to have a positive number. So you can always say that Q reversible minus dQ, or non-reversible process, is always a positive number or less than 0. With that in mind, we can get the dQ to the other side and say that ds, then divide both sides by t to say dQ reversible over t is equal to ds. So the entropy is always greater than dQ over t for an irreversible system. So remember how previous couple chapters we looked at, if we looked at the expansion of a gas irreversibly versus reversibly, the reversible expansion always had greater energy than irreversible expansion. Same thing, a reversible process will always have a greater entropy than irreversible process. Now, but for irreversible process in an isolated system, dQ will be 0. So essentially shows that entropy will always be greater than 0. But how does this work? Well, du, dq, pdv equal tds, pdv. How do those two things equal? Well, negative p external dv is equal to what? D work. Say work is greater than negative p dv. dq is less than tds, so heat plus work is equal to TDS minus PdV. Now, why would we need this? We're going to use this later on in the next chapter to get two new state functions. The idea that heat plus work equals TDS and PdV. But recall how a cyclic integral of a state function will always equal 0. Now, consider the following situation where a cyclic process undergoes a reversible change, but to get back, it must undergo an irreversible change, such as we allow a gas to isothermically expand to equalize pressure, but then we have to actively compress it back. Say, like it's held in place, we allow the gas to expand under a set mass, but to get it back, you have to put a heavier mass to push it back down. So in this case, we have a reversible process one way, irreversible process to get the other way. Essentially, by flipping the signs to get this to 1 over 2 back to 2 over 1 to 1 over 2, we flip the sign to make that less than 0, saying that since Q reversible is always greater than Q irreversible, by making that negative, we say that this number, always being bigger than this number, will always be less than 0, less than or equal to 0. Because heat exchange for a reversible step will always be greater than for irreversible step. And so this is part of why we can't have perfect efficiency, because we can never really, it's too hard to get very many perfectly reversible steps. So we previously stated that entropy is always greater than 0 for a spontaneous process in an isolated system. But what about for a non-isolated one? So just considering the system is always the integral of dq reversible over t. Heat flow is more of an abstract concept. And ds surroundings, the change in S surroundings is equal to the integral of Q surroundings over the temperature of that surroundings. Heat flow is literally the heat absorbed or emitted by the surroundings. That's something we can directly measure. If this is done at a constant volume, Q surroundings can be just calculated as du surroundings. If it's done at a constant pressure, Q surroundings can just be calculated as delta H surroundings. This subtle distinction between delta S system and delta S surroundings will lead us to a concept of delta S universe, or delta S total, that if we add those two numbers together, those will always be greater than 0 for all spontaneous processes. That if all aspects are fully included, delta S total is greater than or equal to 0 always, always. That is truly our second law. That for a spontaneous process in an isolated system, delta S always increases. Well, if we're just looking at the system and not caring about the surroundings, but it's allowed to interact, it's not truly isolated. So heat flow could go in or out, so we could see a negative S. But if we consider the whole universe as part of our isolated system, and delta S is always increasing for the universe, which is the isolated system. Unless we can reach to a different dimension that's outside our known universe, entropy will always be increasing. So let's calculate this. If 1 mole of ideal gas at 273 is isothermally and irreversibly compressed by constant external pressure, 11.2 atmospheres, from 21 liters to 2 liters. This gas chamber is then surrounded by water bath thermal reservoir. What is our delta S total? So it's done at constant pressure, isothermal compression. Q reversible, Q is equal to what? Like nRT, because Q is done at a constant pressure. We're saying that we can say PV equals nRT. We're essentially saying, oh, nRT over V. We talked about this in the previous couple problems of how we get delta S at constant temperature. We have to consider, but we have to say that, well, it's like the work isothermal. So Q isothermal was equal to nRT over V dV. Since all that's divided by T, T's cancel out. So the Q for the reversible system is just 1 mole R 1,4 ln. We go from 2 liters to 21 liters. So entropy of this situation is definitely going to be decreasing for this system. That's equal to negative 19.55. But our heat of surroundings is we can calculate that for this situation. So that's an isothermal process. Heat of surroundings is equal to negative Q over T, which isothermal, we can think of this as work. And work is PdV. PdV over T. So we have P as negative PdV, 11.2, 273, and 2 minus 21. And then times 101 to get this into joules. 2 divided by 273, 19 times 101. So you get what? 78. 78.7 minus 19.5. The net result is an increase of entropy of 59.2 for the whole universe as we do this. So even though the entropy decreases for the system, the surroundings, entropy increases by a much larger percentage. Thus, we see net increase of entropy for the whole shebang. Our last law is our third law of thermodynamics. It states under constant pressure, the molar entropy for a substance at a given temperature can be calculated. The molar entropy. So we start with what is the molar entropy for a solid at 0 Kelvin, starting number, plus 0, we integrate the C sub P over T to our temperature or fusion, and we can calculate the Q over T for fusion, for a phase change. Then we can calculate from freezing to boiling point. So how does the heat capacity change? And our heat capacity, what's our entropy change for vaporization? And we can calculate our heat capacity for a gas to find our entropy for that gas. Essentially, entropy is compounded at a constant temperature as we keep moving from phase to phase to phase and switching physical states. Truly, our third law states that if the entropy of a pure crystalline solid is held at 0 degrees Kelvin, the entropy is 0 if it is perfectly crystalline. What this means is that if there is, remember our thing, entropy can be calculated by Boltzmann's constant, natural log of W, which is our quantum state. Essentially, if there's only one quantum state, meaning perfectly crystalline, and there's no other motions, then natural log of 1 is 0. And so the entropy is always 0 for a perfectly crystalline solid at 0 degrees Kelvin. This gives us something special that we have nowhere else. Delta H and delta U and none of the other ones have a natural 0 point. They only have an artificial 0 point. But entropy can be calculated with a 0 point. And so we can have an absolute entropy where nothing else can have an absolute enthalpy or internal energy. But because of this, we can make a few statements. So because delta S is always positive for these isolated systems, and Cp over T is always going to be positive, we can say that the entropy of a solid is lower than the entropy of a liquid, which is lower than the entropy of a gas, because we keep on adding portions onto this. Because of the nature of this, molar entropy will always increase with the size of the molecule, because we're going to get greater vibrational degrees of freedom. We're going to increase by 3n minus 6 for nonlinear compounds, or 3n minus 5 for linear compounds. N is the number of atoms, thus contributing to the microstates. The 6 and 5 are removing our translational and rotational degrees of freedom. Solids will only really have vibrational degrees of freedom rather than translational, so it would be even less. But also, entropy is essentially monotonically increasing function of temperature. So it's always going to go up as temperature goes up because of this. Some more quick statements. So how can we calculate the non-standard state of entropy? If entropy is Q over T, well, we also had that, so R ln Vf over Vi, or negative R ln Pf over Pi. So if we have the molar entropy and we want to find it at non-standard pressure, we take our standard state entropy and add on the effective pressure. Or we could add on the effective volume, depending on what we're looking at. And the entropy of a reaction can be calculated just the same way as the enthalpy, where we have to have the enthalpy of a reaction is the sum of VI of SI for each reactant and products, where V is the reaction coefficient. But easier way to calculate this at other times, and we can also calculate entropy at temperatures other than 298. We can say delta S at 298 plus integral from 298 to whatever temperature of C sub P over T, ut. Of course, if it's a reaction, we have to do the whole sum of all the CPs again. I know a total pain, but totally doable. This last problem is going to be just that. Okay, so let's start by calculating the entropy of this combustion of methane. First at 298. So S is going to be equal to 188.8 times 2 plus 213.8 minus 186.3 minus 205.2 times 2. All right, now I got the first part is negative 5.3. Want to look at this? Yeah, that looks about right. Now C sub P is going to be a bit bigger pain in the ass. So we're going to do each part in turn. 33.8 times 2 plus 18.86 minus 30.65 minus 32.83 times 2. Negative 9.85. Next one, negative 0.00795 times 2 plus positive 0.07937 plus, it's plus a negative 0.01739, and then plus a negative, so what, minus a negative 0.03633 times 2. So plus 0.5352 T over T. So that. Now, next one, 2.8228 times 10 to the negative 5th times 2 minus 6.7834 10 root negative, oh god, 8228 times 2 plus negative 6.7834 negative 5 minus 1.3903 10 root negative 4 minus 1.1532 times 10 root negative 4 times 2. I'm going to double check this before I go on to the next step, but okay. 0.0381048 T. And the last one, oi, right. 3115 times 10 root negative 8 times 2 plus 2.4426 times 10 root negative 8 minus 8.1395 10 root negative 8 plus 1.2194 times 10 root negative 7 times 2. Positive 1.6 1.6068 times 10 to the negative 7th t squared. Just want to double check before I continue. 5.3, 1.6, and 81, fourth. Okay, it says here I got a slightly different number. Let's check the second one, which is why I checked this. So negative 0.00795 times 2 plus 0.07937 plus 0.01739 plus 0.03633 times 2. I'm thinking I got the same number again. I'm going to work with my number there, but either there's a typo in my equation up there or a typo down there. It doesn't really matter. I'm going to make a small change. We'll figure it out. So integrating this, negative 9.85 integrated to natural times natural log of, going from 373 from 298. So 373 over 298, negative 2.21. One's 1.15352. 15352 times 93 minus 298, positive 11.51. So that's going to be a little bit of a different one. Negative 3.8100 81048 divided by 2 times the difference between 373 squared minus 298 squared, negative 9.588. And the last one, 1.60681 times 10 root negative 7 divided by 3 times the difference between 373 cubed minus 298 cubed, positive 1.362. So 1.362 minus 9.588 plus 11.51 minus 2.21, 1.074. So we add that on, 5.3. Entropy change becomes negative 4.226. Slightly different from what I'm going to show you next, because, as I said, a slightly different number. Not big of a number. But I need to double check those numbers. But okay. So saying that combustion might be a little bit more spontaneous at higher temperature, or they're saying a little bit of the opposite. The last major thing here is talking about refrigerators, heat pumps, and real engines. So we began this chapter looking at the Carnot cycle. We'll end it by returning to it. Carnot cycle transferred heat from a hot reservoir to a cold reservoir, and the process extracted work. What would happen if we were trying to reverse this process? Well, you'd get a refrigerator or a heat pump, depending. The refrigerator extracts heat from the cold compartment, which is our system, expels it into a hot compartment, which is our room, our surroundings. The heat pump just extracts heat from either a cold light or ambient air outside the home, which is our surroundings. It inserts it into a system. You turn in work to heat transfer. In neither case, this is not fully efficient, but it's still far more efficient than turning work directly into a heat. Like if you try to use a electrical heater where you run electricity over a resistor and try to heat up the room, it'd be far less efficient than if we try to use this engine. Transfers heat from a cold system or cold surroundings into a hot system. Possible to do that, but once again, not spontaneous, so it needs work to do that. The other things are the auto engine. Auto engine is actually a kind of the true automobile engine. It's not quite the Carnot cycle, but it has the same general process. And that, how does this differ is that auto engine uses we allow a reaction to occur rather than an ideal gas. So the first step is so we allow fuel to flow in as we allow the engine to expand. And then as a downward stroke, it compresses this. At this point, we do a spark, which causes this to heat up and starts to expand. So the downstroke or power stroke, and then as it compresses back up, we allow the gas to leave. So essentially starting with one, we have intake stroke where there were very low pressure, very low volume, and we expand the volume while we add more gas, keeping the pressure the same. From there, that's where we start to do the work with the compression stroke. We're compressing this down, and then we combust it. So we're there's the isothermal step. Well, not isothermal, isoenthalpic step, where heat is not transferred. We're allowing the gas to heat up and it starts to expand. The pressure goes up. Or the pressure goes up without expanding, and then downstroke, where we get all the energy as the pressure decreases, as the volume increases, and then finally we allow this to, so the pressure goes down a little bit further as we're kicking this out at a constant volume. And then we start to we have to get the exhaust stroke, so we're pushing it out again. So heat is being lost here, and then we go. So that is essentially how the engine works. We have a two-stroke cycle. So going in, goes around, and goes back to get back to the original starting point. Now, a diesel engine works very similar to the Otto cycle, but one key thing. While the last guy had a, let's go back, see right here, step 3 and 4, where it's a constant volume process, the combustion process, constant volume, but pressure is allowed to increase. Whereas here, this from 1 to 2, we have the 3 to 4 is now a constant pressure process. So how is this working? Intake stroke, only air comes in on the intake stroke. We have a liquid fuel in here. We're not having a gaseous fuel. Of a heavier liquid fuel that's already there, and only air is coming in on that intake stroke, which allows us, when we compress this adiabatically, we can get to a much higher temperature without fear of auto ignition, so we don't accidentally burn. So we get to a higher temperature. So when we burn this, we keep the pressure the same and start to increase the volume a little bit. Or, oh, sorry, yeah. Intake stove here, the fuel comes in, adiabatic compression, and then from here, from B to C, that's when we allow the air coming in. The volume expands just a bit to keep the pressure the same as the volume increases. And then the power stroke is we combust it right here at C and we jump down. We go back down, exhaust, downstroke, exhaust stroke, and then intake stroke. So the idea here is that we can heat this up to a much higher temperature before we put the oxygen, and ignition occurs without the need of a spark plug. This remaining step then the remaining steps just mimic the auto engine. Now, the big idea here is that because we can get to a higher temperature, we have a higher hot reservoir versus the cold reservoir. This higher hot reservoir means greater efficiency. So an engine that runs on diesel fuel gets high hot reservoir and thus higher efficiency engine, and thus we have usually greater miles per gallon for this guy. That is end. So thank you very much for your time. Please like and subscribe. Okay. Have a nice night.